Mark P. Otten back with you.
Okay, this is your Psych 534 interaction effects video. Let's get right into it. So, basically we're going to review interactions briefly here, very briefly. You guys have probably studied interactions before in the two-way ANOVA context. We're going to transition that to the regression context, and then we're going to transition that to the structural equation modeling context. So we back up first. Basically, what you're doing here is what is very common in psychology research. You're testing the effects of one variable with the other second independent variable in mind. Those two variables are interacting to produce changes in the dependent variable. Again, I won't go into that in too much depth here, but I'll give you a quick example. This is the one that I use when I teach my 320 introduction to this kind of thing. 320 is the intro stats class. What do I tell them? Well, I tell them that there was once a study that was conducted by students who I was like a TA for when I was back at UCLA. They actually ran this experiment even though they didn't have very many female participants. They actually ran this experiment where they tried to figure out if someone walking into the room would do more jumping jacks in front of a male versus a female experimenter, and whether that person's own gender would factor into the equation if those two independent variables would interact. So this is a sample of four means that you might see in a familiar looking 2x2 table. IV1 on the rows and IV2 on the columns, or vice versa. And the dependent variable, the numbers represent means on the dependent variable, in this case number of jumping jacks. And so here we're seeing that the female experimenter has inspired a great number of jumping jacks coming from the male participants. So we can also do this in the multiple regression context. Of course, that was the quickest review of a ANOVA interaction ever. But usually there are some graphs that are associated with it. You can look at the parallel lines on that graph to determine something, whether the interaction is there or not. And then there's also p-values associated with those things, with those effects. Typically you test for two main effects and one interaction when you have two IVs. So in the multiple regression context, what does all that look like? Well, first of all, they don't always call it an interaction. They call it a moderation effect. And the moderation implies sort of a sequence where you have an initial IV, and then you add in a second IV, and that second IV changes the impact of the first IV on the dependent variable. Well, that's the same thing as an interaction. Interaction, when you do one in ANOVA, a lot of times you have both IVs in there from the start. That's really the only difference that I can see in terms of what interaction effects are versus moderation effects, in that sometimes for an interaction you hypothesize something from the beginning and you have both IVs in there at the beginning and all the way through. For moderation, you could do that, or you could have the first IV in there and then sort of as step two add in a second IV that will then moderate or interact with the first IV to produce changes on the DV. So either way, we're testing the same thing ultimately. And we are, to do this in regression, and this is the part where maybe you guys have seen this before, maybe you haven't. This is the transition period of this lesson where we transition to regression. So you take your multiple regression here, your typical formula with the two IVs in there, and you do something to it, and that something is multiplication. So this is what the typical multiple regression starts out as, with two IVs, and then this is what it looks like if you're interested in the interaction between the two IVs. So you're multiplying x1 and x2 together, which looks a little bit unnatural. There's a couple things we need to do in order to make that happen. You can't just multiply them straight out. You have to do something first. So I'll tell you what that thing is. But it also, in putting this in interaction terms, or two-way ANOVA terms, like before when we just had two IVs here, without them interacting, basically you're just testing two main effects, right? You're testing the main effect of IV1 and the main effect of IV2. Now you're doing the same thing, but you're adding in the interaction, which seems kind of standard in terms of if you're used to the ANOVA context, but doesn't seem so standard in the regression context. And so that's why this is important to cover here first, because something like this is going to happen when we get to SEM interactions. Okay, so what do you do in order to multiply those variables together? You center them. Again, this may or may not be familiar to you from the past. Centering is basically just multiplying two variables together. Well, it's what you need to do in order to prep your variables to be multiplied together. That's what I should say. So the centering process is just to take a deviation score and then not divide by the standard deviation. You could divide by the standard deviation, actually, if you wanted. That part is optional. So instead of standardizing a variable, you're centering it by just making sure that the mean is 0. And that's important because then when you multiply together two variables, like 0 times 0 is 0, meaning that if somebody's at the mean on both IVs, then they're also at the mean on the interaction term. And that needs to be in place because then the math won't work without it. So that's the short answer anyway. So again, it's like standardizing, but you don't have to divide by the standard deviation. And you can do this. There's various methods of doing this through Excel and SPSS that we can talk about if you'd like to do this and not have to spend a lot of time on it. You don't have to necessarily do this for one person and then do it again and then do it again. You can do some copy pasting in Excel or some other method. So again, we can talk more about that if you're interested or if you're stuck on how to do this. But meanwhile, I said here in SPSS you do it. In SPSS you could go to transform and compute variable, and then that would be after you find the mean. You would find the mean by some descriptive statistics, and then you would take that mean and have it be subtracted from each value, and that would form a new column, which would be the centered version of x1 or the centered version of x2, something like that. Once you have those, you would multiply them together, and you'd have a third. It would be x3, and proceed from there. So this is going to be the example we run through here. This is a developmental psych example. I actually worked on this project in the past with Ted Hutman here, who I actually went to grad school with originally. And so he looks, and he works at the UCLA Center for Autism Research and Treatment. So that's where this data was collected. 173 children, very large sample size, lends itself well to fancy analyses here. Very large in the sense that it may not be always easy to find large sample sizes when you do autism research. So his hypothesis was the following. So he had two IVs, verbal skills at 18 months. What is that? That's a year and a half old, verbal skills at that age, then predicts language acquisition at 24 months, which is 2 years old. So that's the first prediction there. You're predicting that verbal skills at a certain level of development will then predict language skills later on. So that's number one. You have IV, verbal skills, DV, language acquisition. Number two is the interaction part. So this is only true for children with low severity of autism symptoms. So you're adding in a second IV and you're putting a condition on that first IV. So the second IV here then is severity of autism symptoms, and you're saying that the prediction about verbal skills leading to language acquisition is only true for those children with low severity of autism. Now the key statistically here is how are we measuring these things, right? So if we have verbal skills as, let's say, high and low, and then we have autism symptoms as high and low, right? Then those are categorical variables. It's a nice little two-way ANOVA. We can make the graph, we can assess the main effects and do all the usual things. However, according to Ted's data, verbal skills is actually a continuous variable, and severity of autism symptoms is also a continuous variable. So we're allowing autism symptoms to moderate or interact with verbal skills, and both variables are continuous. So one solution then, and this is what a lot of psychology researchers might be tempted to do, is to dichotomize these variables. And I've talked in past lessons about how dichotomizing variables is a little bit tricky because you lose variance. When you dichotomize, you're sort of lumping in all of the moderate to high severity autism symptoms, let's say, together into one category. Same thing with low or none in terms of autism symptoms. That would be all one category. if the variable was dichotomized. So it's a little bit like restrictive, and you don't necessarily benefit from that. You might even prevent your conclusions from turning up interesting results by doing that. So generally that is done a lot, but it's also not recommended by statisticians. Generally, it's not never recommended, just generally not usually recommended. So we leave them as continuous variables and we proceed with our interaction or moderation analysis via regression. So what does it look like? Well, here's our IV number 1, IV number 2 that I mentioned, the dependent variable language acquisition. We start with our standard regression formula. This is the one that does not include the interaction. So here's our unstandardized coefficients for this particular equation. Now we add in the interaction term, and so we've got B3 there to assess the multiplied x1, and again centered, but multiplied centered x1 with centered x2. And we get an equation that looks like this. Now what does this mean? So this is the key, right? We now have a 1.23 for that interaction. What does a positive mean for that slope value? What does a negative mean? It's a little bit cloudy now because we have a multiplied variable that is not so cleanly interpreted. If we go back to the original equation, we see a positive slope for x1, which was verbal skills, which is consistent with the first hypothesis that verbal skills may impact and positively impact language acquisition. The negative slope there for x2 is the greater the severity of autism, the worse the language acquisition, the slower the language acquisition. So those are your main effects. Then we add in the interaction. We still have a positive slope for the first effect and a negative slope for the second effect. So those main effects are intact. And then, like I mentioned, we just have that new slope, the 1.23, for the interaction that needs to be interpreted. So
to help with the interpretation, we consult Leona Aiken and Steve West. By the way, Steve West, who was at Arizona State, he took a 1-year thing and was at UCLA teaching classes for 1 year, and he taught a class one time that included graduate students Mark P. Otten and Andrew Ainsworth in there. So anyway, I took Steve West's class one time and learned a lot, actually. So to help in this case with interpretation, we go to I went to their book. Doctors Aiken and West have a regression book that has lots of details. It's actually an interaction book. Lots of details on how to analyze and interpret interactions in the regression context and as an extension of the ANOVA context. So I went there for help with interpreting these regression interactions, and they recommend we make some graphs, which I will show you for our example in a minute. First, you find the mean of x2. x2 was severity of autism symptoms for us. Well, of course, we already we centered that variable, so the mean is going to be 0. And then you just go and find the standard deviation, and you go above +1. You go +1 and -1 on that standard deviation. And then for each of these values, you make a graph. And so I'll show you what the setup was here for our example. We have, like I mentioned, x2 severity of autism symptoms. The mean became 0. The standard deviation 1.726. And so then you plug in 1.726 into this equation. This was our equation that I just showed you with x1, x2, and then the interaction term all in there. So you start with that and you plug in that standard deviation value for x2. You plug it in twice, and then it simplifies. So you, like, for example, in that second term, it's minus 1.15 times x2. That becomes minus 1.15 times 1.726. And then it goes in also in the interaction term there. That first term then gets simplified, so 1.15 negative times 1.726 becomes negative 1.985 in the third line there. And then that gets subtracted from 25.24, which was your intercept value, or your A value there. And so you end up with a couple ways you can simplify this down based on the fact that you plugged in that standard deviation value for x2, and you end up with the equation down there at the bottom with your new regression coefficients and just one x1. Now x1 is your only x. And then this is the version where you have the -1 standard deviation, which is minus 1.726. And so you plug that in here instead of positive 1.726, the values change and you end up with the equation down there in the bottom. Again, according to this example. So you've got two equations now and you can plot these in Excel. Okay, so here's what it looks like in Excel. You've got on the left the children 1 standard deviation above the mean on severity of autism symptoms. And then on the right you have the children below the mean by 1 standard deviation. And you can contrast these two graphs. So the way I set this up in Excel is I set up this little sample data set. This is just like I chose x1, 0, x1, 1, and x1, 2, and then I just plug those into the equation. This is just to allow us to get a straight line out of it. So for example, this first one, if x1 is 0 in this equation on the left, you've got just 23.255, right? Because the 0 times 2.673 comes out to be 0. If you plug in 1 for x1, you're going to get 2.673 times 1 plus 23.255, and then you do the same thing here, plugging in 2. You actually only really need to do this with 0 and 1, but Excel was being weird, so it required me to put in a third value there in order to get this graph. So you get those three values, x1 and y combinations. Then you highlight this out, and you go to Insert Chart, and I'm on a Mac here, but I'm pretty sure it's going to look somewhat similar on a PC. You're going to go to scatter plot there. So I went to Insert, and then there's like a little icon that suggests a scatter plot, or you can go to Insert at the top of the screen, and you'll have a slightly different looking menu. Anyway, you want the one that plugs in the line as opposed to the dots, because the dots are just going to be in a straight line in this case. Again, this is all just to illustrate or allow us to draw a straight line based on our regression equation. And so I hit scatter with smooth lines, that's what it's called, I guess, and it gave me this graph down here. And then I did it twice, once for the 1 standard deviation above and once for the 1 standard deviation below. And then I made a little conclusion at the bottom. You can contrast these two graphs because, I mean, you can see one of them has a slope going up and the other one has a slope going down, and that's because of that slope value in the equation. One of them's positive and one of them's negative. So on the left, it looks like a positive slope, and the conclusion is that the greater the verbal skills at 18 months, that's your x1, the greater the language acquisition at 24 months, that's your y. So you've got an x1-y relationship for folks 1 standard deviation above the mean on x2, severity of autism symptoms. Then on the right, you've got the one going down. So the greater the verbal skills at 18 months, x1, the lesser the language acquisition at 24 months, because y is going down with x1 going up. So that's the negative there. And maybe that has some meaning for you if you're a developmental or child psychology researcher. But statistically, you've got a difference now, and so you've got something suggesting that you have an interaction between x1 and x2, and this is the illustration of that. Of course, the missing piece is then to go back to SPSS and get your p-value that corresponds to that interaction to see if it's actually significantly a difference here between these two lines. So like the lines could appear to be non-parallel in this case, and you would still have a non-significant interaction. So this is not a test of that, but it is an illustration of the situation we have. And the other thing I'll mention is that if we're following the Aiken and West book most closely, we're actually probably doing a third graph for children at the mean as well, just so we can contrast them too. So it'd be like 3 graphs instead of 2, but in your assignment that I'm giving you, I'm only requiring 2 graphs, so that's what I did here. And it gets you going. It gives you the idea of what might be required in this situation.
So what happens if one of your IVs is categorical? Well, actually, this is kind of what we just did. We made our second IV into a categorical variable, right? Severity of autism symptoms. We did the mean, 1 standard deviation above the mean, 1 standard deviation below the mean. So we left it as a continuous variable initially. We made our regression equation, and then in order to illustrate it, we made those 3 lines as a result. So if your second IV happens to be categorical, your work is done for you. You don't have to do the plus and minus 1 standard deviation trick. Okay, so this is the transition now to graphing for structural equation models. So for structural equation models, the first step is to center your measured variables. This is attributed to Kenny and Judd. That's the same David Kenny who has studied and published on mediation methods and strategies over the years. He was a busy guy in his career. But anyway, testing of interactions it's basically the same thing that we just did. You just need to make latent variables the same way we've been doing for structural equation modeling, but center each of the measured variables first. So let's build on our example here. This is what Ted and I actually did in our research, or this was my analyses to supplement his research. So basically, we have verbal and nonverbal skills. So you might imagine a child at 18 months might have certain skills that are verbal, and perhaps even more, a wider assortment of skills that are nonverbal at that age. So we're adding that in, and then we're going to make some latent variables here. The rest of the hypothesis is the same, so that skills in general, verbal and nonverbal, are predicting language acquisition, but only for children with low severity of autism. So there's various ways we could set this up, but this is what we actually did in real life, so this is what I'm showing you. Again, verbal and nonverbal skills is the first IV now, just instead of verbal skills. We had 4 indicators there, 2 forms of measurement of nonverbal and 2 forms of measurement of verbal skills. Those then composed a skills latent variable with 4 total indicators. The second independent variable was still a measured variable. We only had 1 assessment of severity, so we left that as a measured variable. And then the DV was also measured in the same sense. So we're really creating 2 latent variables here, and we're starting with 1. So the one that we started with, I just described, was the skills at 18 months, a latent variable with 2 verbal and 2 nonverbal skills. Then we have this skills autism interaction. So what we're doing here is we're doing the same thing we just did, but we have 4 indicators, 4 measured variables of representing skills. So that's like 4 multiplications now. Autism severity is sitting there by itself as part of our model. That's our moderator, or the variable, the second IV that's interacting with the first one. The first one now is the skills latent variable. And as you can see here, we are multiplying each of the measured variables that compose the skills factor. We're multiplying each one in turn by autism severity. So you're also centering autism severity as you did before, as we did in our example before. So it's centered verbal 1, that's our first measured variable, multiplied by centered autism severity. That then composes your first component of the skills autism interaction latent variable. So you're actually having 2 latent variables there instead of 1 in the end. You start out with skills, and then you have this skills autism interaction factor that forms as a result. I also put the plus and minus in there. Skills positively predicting language, and the negative is the autism severity negatively predicting language acquisition. And I did not put a sign prediction in for the skills autism interaction because, again, it's kind of hard to interpret that slope, that b or that beta that comes out of that equation without doing some graphing. So what you can do, however, is look at the significance of it, like I mentioned. So there's going to be p-values associated with each of these, and we can assess them in turn. So again, graphs are recommended. We're going to not do this in class, most likely. We'll see if we get to it. We're going to start with the regression one and go from there, because that's a little bit cleaner to interpret. But we can do this again if it helps with our interpretation. Basically, like I said, you're going to get a p-value that's associated with that skills autism interaction predicting language acquisition, and you're going to know whether the interaction is significant or not. And then to interpret, again, it's making some graphs. So here you're again finding the mean of x2, which is autism severity, and one standard deviation above, 1 standard deviation below it. and then for each of those values, graphing your X1 relationship with the DV. In this case, the skills latent variable predicting language acquisition. Okay, so meanwhile, we'll run our SEM before we interpret. Let's run it first. One thing to note is that the product variable, so the latent variable we created where we multiplied autism severity here, not there, autism severity multiplied by the skills latent variable. That one is not going to be, you can't assume that's normally distributed anymore. It might be, but it might also not be. And so that's even if both of its components are not normally distributed, or even if both components, that is skills and autism severity, are normally distributed, you cannot necessarily assume that the multiplied variable is, because, well, when you multiply two things together, you're going to get something that may or may not make sense in terms of, oh, this child has high skills multiplied by autism severity. That doesn't make sense. So anyway, when you do that multiplication, you have to then realize that that variable is a little bit strange in its descriptive statistics that you might generate for it. In this case, it would be the descriptive statistics associated with those 4 measured variables that compose the latent variable. So this, in the end, what this means is that we just switch. We switch out of maximum likelihood estimation, which is normally the default for SEM in generating your model covariance matrix. You switch out of that, and then we follow Kenny and Judd again, who recommended the generalized least squares estimator. We talked briefly about the GLS estimator as an alternative to maximum likelihood in a previous lesson. There are a number of these as alternatives, and this one just does not. The key here is that it does not assume normality among all of your predictors, all of your variables. So we switch over to that one, and so you can go ahead and run that in R instead. Just look up the code, or we can give you the code to switch over to this method of estimation. So we'll do that here, and then we'll get our numbers. Let's see how it looks. Okay, here's how it looks. Not a lot of stars in there. I didn't put in the significance values, but we can trust that those error variances are significant over there on the left side, all pretty large. Mainly what we're looking at here is the interaction. So we have a main effect for skills that appears to be positive as predicted, but not necessarily significant. Autism severity dropped way down to non-significant, and then the interaction itself was also non-significant. So again, this was real data. I'm giving you the real story in some sense, that this did not come out. We did not end up as famous published authors for this study. At least this portion of the study did not come out to be fruitful. So the 0.07 there suggests, and the p-value associated with it suggested a non-significant interaction. So we would report that, and then we can also report our usual fit indices and things like that, make the necessary post hoc adjustments. Here it might be suggested that we could drop the 0.07 and not have a significant drop in model fit. Before I get to the conclusion here, let me go back to this model. So basically, we like I mentioned, if you do get a significant interaction there, you might want to follow up with some graphs. Here we could also follow up with some graphs. We get a 0.07, let's say, p-value not less than 0.05. What do you do? Well, you could make those graphs that I was talking about. You could put autism severity at the mean, plus or minus 1 standard deviation, create 3 lines for the skills latent variable to predict language. You could do all that, and then what you'd probably find is that the slopes of each line all look kind of similar, right? And if they're all kind of similar, then, well, autism severity is not changing the relationship. It's not interacting with skills in order to produce some sort of difference depending on a high or low autism severity. What that's going to tell you is that the skills-language relationship is actually fairly consistent across different levels of autism severity. So in this case, you could make that graph. It would just be 3 lines that have relatively similar slopes. And so then that would be illustrative of that lack of an interaction as well.
Okay, so in conclusion, the first thing that we did was we tested for an interaction between a latent variable and a measured variable.
The second thing is that we can also test for interactions between two latent variables. So suppose you go back here and suppose in this case we had autism severity as a latent variable with multiple indicators. We would then center those indicators and then multiply. It would basically be an expanded version of what I'm showing you here. When Ted and I were putting this together, we considered that because he did have another measure of autism severity, but I was like, well, let's just stick with this first one. He agreed that it was a good measure, an accurate measure, the best he had. So then we stuck with it for simplicity. But simplicity has never stopped anyone from running more intense, more interesting analyses here that might be the advantage of turning something into a latent variable, right, is that you're measuring it a little bit more precisely, right? You're doing a little bit more to combine those components together in a way that's informative. So if that were the case, if that had been the case for autism severity, we would have done that, and then we would have expanded out this diagram and had even more fun with SEM. So if you're interested in doing something like this in the future, feel free to talk to me about it. You can also check in with Rex Klein. The Klein book I haven't mentioned much yet, but there's a lot of detail in there as for some of these scenarios regarding interactions. And then this book will also be useful as we go through the rest of the semester because it's going to give us some information about some of the more advanced variations on SEM. But meanwhile, we'll pause there.